Welcome, dear students, to the next module, the module number 4. So, this module is regarding forging and drawing and extrusion. And the first area we are covering is forging. So, we know in the last lectures we discussed the metal forming. In the metal forming, and the one example is rolling process. In rolling process, we deform the material plastically to convert the raw material into a particular product. So same way, in the forging operation also a plastic deformation process. Okay, so in this plastic deformation process, we know how much amount of stress is required. In the stress strain diagram, we should apply a stress which is at least greater than equal to the yield point of the material. Okay, so if already deformed material, for example, if you have a raw material which is already deformed with a epsilon 1 strain, then we need to apply a stress equal to epsilon 1, that is the flow stress of the material for further deformation of the material. Okay, so here in this forging operation is also a permanent or plastic deformation process. What is the difference between a rolling and a forging process? Here we apply a compressive force. In case of rolling operation, we actually fed the raw material through the gap between the rollers and then we deform the material. Okay, but here using a set of dies, we apply a compressive force into the material, and by means of this compressive force, this material is plastically deformed. Okay, so then we can convert by this process we can convert a raw material or a raw product into a final product. Here we can see we can make different components, varieties of components we can make with the forging process. Actually, the forging is evolved in 5000 BC. It's a very oldest metalworking process. Commonly, we know in our village, blacksmiths are usually use this process, the metal forming process or forging process, to convert the raw material to a required product. Okay, but in blacksmith they use hammers for or hammering process for this forging. Okay, they have a workpiece and they hammer on the workpiece, and by this impact force the workpiece is converted to required product. Okay, that is commonly used in blacksmith. Okay, so the same process nowadays after industrial revolution, this process, this hammering process used by this blacksmith is converted to a what is as an industry process. Okay, so we mechanize the process actually by means of different machines. So nowadays we are creating very small bolt to very large turbines with the forging process. Okay, it is a mechanized process. We have different set of machines for forging operations, and using these forging operations we can create varieties of shape. Even we can create very complex shape also. Okay, and we can say the crankshaft. We know the crankshaft is a very complex shape, and connecting rod for the engine. See this the connecting rod for the engine. Gears with the number of teeth over the periphery. So actually it is a complex shape. So we can create gears using forging process. Bolt head. Actually the bolt and other fasteners commonly made with this metal forming process. They are industries not using or rarely using this machining process for the creation of fasteners like bolt, screw, etc. Bolt, screw and other similar fasteners are commonly made using metal forming or especially the forging process. Then hand tools and the other structural components also can be made using forging process. See these different products made with the forging process. Okay, or we can see very complex profile surface on these products. So we can make all these products with a minimum time. That is very important. The production time for the making of these products is comparatively minimum than any other process. Okay, for example, if we want to make a connecting rod. So for making a connecting rod, my machining process, it will take very huge time for the machining. but we can make the connecting rod within minutes using this forging process. Okay, so that much productivity we can ensure using this forging process. That is the advantage of the forging process. So here what we do, we apply the compressive force. How can we apply the compressive force? There are two methods for applying the compressive force on this workpiece, either by hammering. Okay, the hammering may be a manual hammering, or by an automatic machine we can hammer this workpiece. Okay, so actually hammering means we supply some amount of impact force on this material. Okay, so by means of impact force or hammering we can apply this compressive force. Okay, and second method is by pressing. So we kept the workpiece in between two dies and then we press the workpiece. Okay, so here in this pressing we gradually increase the load. It is not an impact load, we gradually increase the load during the pressing process. So these are the two common methods used to apply this compressive force for the plastic deformation. So this compressive force should be equal or greater than that of the flow stress of the material for the permanent deformation. Okay, so we already studied the plastic deformation. In case of plastic deformation, we should apply a stress which is greater than the flow stress of the material at a particular strain. Then only we can permanently deform the material into a required shape. So that is very important. So we already discussed this advantage and disadvantage of the metal forming process in the third module. I am not going to repeat this. Just refer the previous lectures for this distinguishing of the advantages and the disadvantages. So here in this simple forging process, I already explained that we use hammering. Okay, we use hammers and anvil. Commonly, blacksmiths use this technique, hammering, for the conversion of the material to raw material to finished product. So here we supply impact force, and this is called hammer forging. Then in case of press forging, the other type is press forging. In case of press forging, we slow speed compressive force is applied on the material. Slow speed compressive force. There is no impact force on the material. So actually, when we do forging process manually by blacksmith, they should apply the impact force. Okay, they cannot deform the material by a pressing. Slow increasing compressive force or slow pressing, they cannot deform. In case of manual operation, we should apply the compressive force by means of hammering. Okay, but in case of machine forging, we can use either hammering or a pressing for the forging operation. Okay. So next we will see a video. This is actually the entire explanation of the forging process in this video. So listen to this video and
forging is the control.
See, this is the forging operation. Here we can see this is the bottom die. We can see some cavity on the bottom die. So there are 3 cavities in the die, and similarly on the upper die also the similar cavity will be there. Okay, so by means of pressing or hammering action or impact action, we can deform the material. So this is a hot working process. We can classify the forging process into two, basically the cold working forging process and a hot working forging process. In case of cold working, the material will be in a room temperature, but here in this case we can see the material is in the hot condition. So this is called hot working process. Okay, so we heat the material above recrystallization temperature in case of hot working process.
Controlled deformation of metal into specific shapes. Forging is the controlled deformation of metal into specific shapes by the use of compressive forces.
This is an example for impact forging or hammering forging. Okay, so this is another machine which is a hammering forging.
These forces are applied through tools and dies.
So certain impact force is applied for the plastic deformation in this case.
Driven mainly by hammers, which deform the workpiece by high velocity impact. Or
so here high velocity impact is utilized for for supplying the compressive force on the material for the deformation. So next we can see the press forging. In case of press forging, what is the difference? In case of press forging, we apply the compressive force in a very slow speed, but constantly actually the force is increasing. Constantly the force is increasing, but we apply the force very slowly. Or we can say in another term we can use, that is strain rate. Okay, so in case of press forging, the strain rate is very low, but in case of hammering forging, the strain rate is very high.
Presses, which deform
this is press forging.
The workpiece through controlled high pressures. Forging is one of the
So this is the oldest process. Blacksmiths are commonly use hammering process for converting the raw material into a finished product by metal forming.
Oldest metalworking processes, dating as far back as 8000 BC. It is utilized today to reduce the cross-section, improve the metallurgical microstructure.
And again, forging is divided into two. The first one is open die forging, and second one is impression or impression die forging. Okay, these are the or closed die forging. Okay, two classification for the forging again. The first one is open die forging, and second one is impression or closed die forging. So this is an example for open die forging. Here we can see this is my top die, this one is my top die, and this is the bottom die. Okay, so we kept the workpiece in between top die and the bottom die, then we apply the compressive force. And here we can see in this area there is no member to restrict the flow of material laterally. The material can easily expand in this direction. Okay, there is no restriction for the movement of material in this two direction. But in this direction, here in this two direction, there is a restriction offered by the two upper die and bottom die for the material flow. So here in some region, in open die forging, in some region, there is no restrictions for the material flow. So such type of forging is called a open die forging. So this is an example for open die forging. Okay.
Provide directional grain flow and eliminate porosity of cast ingot in fabricating wrought mill forms, and to form discrete parts to near net shape from these wrought mill forms, further refining microstructure and directional grain flow. Because of these effects on microstructure and grain flow, the mechanical performance of wrought mill forms.
So see the microstructure. See the microstructure. We can see the grain flow pattern in this microstructure. See this. This is a forged part, and this a particular directional grain flow change, or it has an influence on the mechanical properties of the final product. I will explain about that later.
Structure and grain flow, the mechanical performance of wrought mill.
See this. This is the next example, that is the closed die forging or impression die forging. In case of impression die forging, we can see here in this die we can see a cavity. See this, we can see a cavity in the bottom die. Similarly, in the top die or upper die also a cavity will be there, and the material or workpiece is kept in this cavity, and by means of hammering or pressing we convert the raw material to final product. So during the conversion, when we apply the compressive force, the material has a restrictions to the flow in the outward direction. Okay, it can only flow up to the surface of the cavity. Okay, so the throughout this actually the material is enclosed in a particular cavity. So the material can only flow in a restricted place. Okay, so from every direction, there is a restriction for the material flow. So this type of forging is called a closed die forging or impression die forging. So, but in case of open die forging, in some places there is no restriction for the movement of material. Okay, there is no such cavity or members for restricting the movement of material during the open die forging. But in case of closed die forging, we create a cavity or impression, and we kept the workpiece in the cavity, and we deform the material actually by imposing the impression of the cavity on the material. Okay, so that is the method used in closed die forging operation.
Forms and parts is typically superior to that of cast
So this is a casting process. When we compare the casting process and the forging process, we can make same component using casting as well as using forging process. So when we compare the mechanical property of the forged part and the cast product, we can say the strength and other mechanical properties are superior in case of forged component. Okay. So for example, if you are making a bolt with a casting process and a forging process. So when we check the strength, hardness, and other properties of the forged component, we can say the forged bolt has a superior mechanical property than that of the cast product. So that is the advantage of the main advantage of the forging process than that of the casting and other similar primary shaping process.
metals. Open die forging.
So this is an example for open die forging. So as I said, there is no restriction in the lateral direction in this direction for the material flow. This is an open die forging, and this is another name. This process is called, and there are different forging operations. This process is called upsetting process. Upsetting process
is performed on ingot, billet, bar, or a preform, and is the deformation of a workpiece between flat or shaped dies without completely restricting metal flow. This deformation can result in lengthening of the workpiece while reducing its cross-section.
See, this is another example for open die forging. Here we are not providing any restriction in this direction, so we can say this is a open die forging operation. Okay. And as well as it is a hot forging operation, the workpiece in the hot condition.
Upsetting regions along the length to greater sizes than adjacent regions, or bulging the workpiece's cross-section while reducing its length.
This is a press
Lengthening
forging
and reducing its length.
This one is a press forging. We can see there is no impact force acting on the workpiece.
The workpiece's cross-section while reducing its length. Lengthening and upsetting are typically done using multiple impacts as the workpiece is incremental.
One more thing is that in case of open die forging, how we achieve the final shape? How can we convert the raw material into finished stage? We have only two flat dies. In case of mainly in the open die forging, we have only two flat dies. So when we apply the compressive force, we cannot achieve the final shape. So that during the process, for example, after first pressing, we change the position of the workpiece, okay, according to the requirement of the final shape. Okay, so in case of open die forging, we can achieve we can convert the raw material into a particular shape by changing the position of the workpiece in between the blows or in between the pressing. Okay, so here we can see this is an open die forging, but after each pressing, we change the position of the workpiece according to the requirement or according to the position or according to the shape we need to achieve during the forging process. See this.
Lengthening and upset.
So this is the first position. Here we apply the compressive force, and after compression, we change the position of the workpiece.
Are typically done using multiple impacts as the workpiece is incrementally advanced lengthwise and rotated about its longitudinal axis.
Okay, so by this way we can change or we can create different profile or different shape on the raw material in open die forging. But this is not the case of closed die forging. In closed die forging, we have already a cavity which is similar to the shape of the final product. So we don't need to change the position of the, or we don't need to reorient the workpiece in between the blow in case of closed die forging. But in case of open die forging, we need to reorient the workpiece in between the flow to achieve the final shape.
There is essentially no limit to the size of forgings that can be made using open die forging. They can range from a few centimeters to 30 meters in length.
See this, few centimeters to 30 centimeters in diameter or size we can use this open die forging. So actually in closed die forging, the main limitation is that for each product we need to make a die according to the requirement or according to the shape of the final product. We need to make a cavity on the die. So that is a costly process. But in case of open die forging, there is no such requirement. We need only 2 flat dies. Okay. So in case of a bigger product, if you want to make see this here, we have a very big workpiece. So if you want to convert, or if you want to forge a very big workpiece, the suitable process is open die forging, because the cost involved in the making of the product is very less in case of open die forging compared to closed die forging. And but the main difficulty in open die forging is that the time, the productivity or production rate is very low compared to closed die forging.
Weigh from a few to up to several 100,000 kilograms. Although fairly complex shapes can be made using open die forging, most are rather simple solids or hollows requiring considerable machining to achieve final shape.
This is actually this figure. This one is the open die forged component. Okay, see the surface of the forged component. This is not a perfectly. There is no finish on the surface. This is not, the surface finish is very low. Okay, okay. So forged component, the main problem of the forged component is that the surface finish is a very poorly one. So we need to improve the surface finish after the forging operation. Okay, so that is the one of the important disadvantage of the forging process. The surface finish after forging process is low. Okay, so what we do after forging, we need to do the machining operations to increase the surface finish as well as to improve the accuracy. Okay,
machining to achieve final shape. Forgings are produced using simple flat, V-shaped, or semi-round dies. Various accessory tools are also used, including saddles, blocks, rings, mandrels, and punches. To withstand forging temperatures, abrasion, and impact, dies and accessory tools are usually made of hot work tool steels or medium carbon alloy steels. Impression die forging.
So this is the impression die forging. Here we can see a cavity on the dies, and actually this is a progressive process. Within a single process we cannot achieve the final shape. So we do 3 or 4 operations in between to convert the raw material into final product. Here in this process we can see 3 operations.
Also called closed die forging is the deformation of metal at forging temperature within one or more die impressions or cavities. It is performed both in presses and hammers. Workpieces may be round or rectangular.
Okay, so in the first block, we convert the raw material into a particular shape. Then we use next die for the next conversion, and then we use the finishing die. Okay, so one product is made with 2 or more or 3 or 4 or 5 operations. Okay.
In cross-section or flat discs, and the dies are sometimes integrally heated to minimize chilling and cooling.
Here 3 operations are used for converting the raw material into final product. Okay, we will discuss about the different operations involved in this forging process later.
Of the workpiece. For simple shapes, impression die forging can be performed in a single press stroke.
If the final shape is very simple shape, then we need only a single operation for converting the raw material to final product.
More often, however, several strokes of different force.
Here there are two operations are there for converting into product.
Are used with dies having several impressions for sequential preforming and finish forging operations. Preforming
this is the procedure for making of connecting rod. So this is my workpiece. So first operation, this is a closed die forging operation for making of connecting rod. So the first operation is this one.
Operations may include.
So this is edging. So first operation, after the first operation, we got this shape. Okay. Then we reposition this workpiece or the semi product into the next cavity, and where we do next operation.
Edging to increase the workpiece cross-section. Blocking.
So on the next cavity, we do next operation. Here, this is called blocking or swagging. Okay. So after blocking or swagging, we can achieve the final shape of the connecting rod. So the operation is not yet finished.
To refine the shape for finish forging. And
then the last one is the finish forging. Maybe a trimming process also will be there. So after the finishing process, finish forging process, we got the final shape or final forged component. Okay, so here in this making, we use three operations. First edging, then swagging process, then finishing process. So we need three cavities. Okay, in the previous video we see there are two or three cavities are there. So after first stroke in this case of connecting rod, we use edging process. Then we place the semi-finished product into the next cavity for the swagging process. Then we place the workpiece into the next die cavity for the finishing process. So we need several such operations for converting this raw material to finished product. But the time taken for each operation is very minimum. Maybe 10 seconds or 15 seconds we can complete the process. In each block, we can do a particular operation.
Finish forging to complete the shape. In finish forging, the bulk of the metal is forced into the impression, while a thin layer.
This is actually happening in the
and finish forging to complete the shape.
Sorry. This is very important. This one. This is actually happening in the closed die forging.
And finish forging to complete the shape.
So see this. Here we have a bottom die. This is the die 1, bottom die. Die 1, and this is the top die. Okay, die 2. Okay, so in between the top die and the bottom die, we have a cavity. See this. This is the shape of a cavity. Okay, so this shape cavity is there for this in between the two die. Okay, so we kept the workpiece. This is a cylindrical workpiece. We kept in between the top die and the bottom die. Then we apply the compressive force. Okay, so when we do the when we apply the compressive force, what happens? There will be a permanent plastic deformation. So the material starts to deform. We can see the deformation here. This is the closed die forging operation.
Forging is the controlled impression. Blanche forging.
See this.
The bulk of the metal is forced into the impression, while a thin.
Okay, so almost material is filled in the cavity, and some amount of material starts to flow in this direction. So this is actually a parting line. Okay, this is actually a gap area. So what happened? Some material starts to flow in this direction because there is a gap area in between. So instead of filling these small sharp areas, see this, these are the sharp areas. Instead of filling these sharp areas, what they do, the material starts to flow through this gap between the top die and the bottom die. So we can see the flow.
Layer called flat.
See this, here the material starts to flow through the gap area, but this area is not filled. Okay, this sharp area is not filled completely. So the material starts to flow in this part, in between this top die and bottom die, and that area is called the parting line area. And we can see
ash
and see this
flows out between.
Okay, so this material is flows out like this, and this is called flash. This is very important in case of closed die forging. This is called flash. Okay, and this flash has an important advantage in the closed die forging operation. The reason is that when the flash is formed, further material flow will not allow the flash. Okay, the flash will not allow further material flow in this direction. Okay, because for the deformation of the flash, high amount of pressure or force is required. Okay, so when the flash is formed, the flash required high force or pressure, so that the flash will not allow further flow of material through this gap between the top die and the bottom die. So the flash will not allow, so that the remaining material fill in the sharp areas. So that is the importance of flash in the closed die forging. So I will explain what is the reason for higher pressure or force required in the flash area in the coming lectures. So now think this, the formation of flash, after the formation of flash, higher amount of pressure or force is required for the further material flow through the flash region. Okay, further material flow through the flash region, high pressure or force is required compared to this region. Instead of the deformation or the material filling in this area, the amount of pressure and the force requirement is comparatively less than that of the material flow in this flash region. Okay, so that the material first fill in this area, entire cavity areas in the sharp corner region, then only material starts to flow through the flash region. Okay.
Between the dies at the parting plane, surrounding the forging. Flash comprises a flat region called the land, and sometimes a bulbous region at the end of the land created by a gutter in the upper die.
This is called land.
The thin flash cools rapidly, increasing pressure within the impression, which and created by a gutter in the
this is called flash. This portion of the flash is called land, and this is called gutter region in the flash.
The upper die. The thin flash cools rapidly, increasing pressure within the impression, which assists metal flow in the impression details. Once finish forging is complete.
So after the finishing process, we can see some amount of material is trimmed off.
Once finish forging.
See this is actually a trimmed material. The finishing process including trimming also. So the remaining material actually in the flash area, some amount of extra material is there. So at the end of the forging process, we trim the extra material.
Is complete. The flash is removed either manually or with trimming dies.
Okay, so that is about the forging process. So grain flow, we know what is grain. In case of a material, we have different types of grains. Okay, inside the grain, the material or the atoms or molecules are arranged in a perfectly regular manner for a long range. That is the grain. Okay, so when we compare the grain flow, okay, we can see the difference in different manufacturing process. In case of casting, there is no such grain flow. Okay, actually in case of casting process, the grain is like this. Actually the grain is like this. Okay, so there is no such grain flow of grains. Actually there is a grain in cast product, but there is no grain flow. The grains are arranged randomly. But in case of, we already studied the rolling process. And when we do rolling process, we apply the force on the compressive force on the material and we deform the material. And during the deformation, the grain flow is like this. There is a particular grain flow in the direction. So this is the type of grain flow. So some amount of grains is not a cut grain, but the grain is deformed and this is a continuous grain like this. Okay, it is a continuous grain. But when we compare the rolled and forged grain flow, okay, the flow of grains is perfect. Okay, true flow we can see in the forged component. So such type of true flow we cannot see in the rolled component. In case of rolled component, there is a grain flow, but in some areas like this, in some area there will be some interrupted grain flow. Okay, but in case of forged components, we can see a perfect grain flow. Every grains are continuous. Okay, so that is the grain flow in a forged component. That is a uniform grain flow. But here this is in case of rolled component, it is not a perfectly uniform grain flow. In some area there will be some non-uniform grain flow or interrupted grain flow. And this is the machined component. This one is the machined component. We can see when we do machining. Okay, for example, when we do machining, the grains actually cut in this region. So this is a cut grain flow. The grain flow broken in case of machining. So this grain flow has a very high advantage or advantage in the mechanical property of the material. Okay, so for example, in case of this machined component, we can see this is interrupted or highly broken cut grains we can see on the machined component. This cut grains actually the region of the stress concentration. So when during the application time, the product subjected to huge amount of force. So when the force is applied on the product, in this regions, the grain cut regions is the region where the stress is concentrated. So this is the one of the reason for the crack generation and a crack propagation, and the finally leads to the failure of the product. Okay, so this types of grain flow in the machining is a cut grain flow. So this is not a good for the for products which is especially which is working in a cyclic operations, like one cycle it may be tension, another cycle it is compression. So that is called fatigue related products. This type of grain flow is not suitable. But in case of this forged component, we can see the grain flow. It is a uniform grain flow. So this type of uniform grain flow has a different. It has a very good advantage compared to all other grain flow, because this uniform grain flow will not allow the crack generation and the propagation. Okay, compared to all other types of grain flow, it has the minimum crack generation tendency. Okay, so that is the advantage of the forged grain flow. It has a uniform grain flow. So this is the this one is for casting, and this one is for I think this is for second machined component, and this third one is forged components. We can see a flow of grains here, flow of grains, but here in this region the grains are cut in case of machining. Okay, so this is a fibrous microstructure. We can see the grains is actually flowing like a fiber. Okay, so this gives better mechanical property in the plane of maximum strain, but lower across the thickness region. That is also important. This types of grain flow in the forged component actually gives anisotropic property for the material. We know what is isotropic property and anisotropic property. In case of isotropic property, in every direction the strength or other properties are same. But in case of anisotropic property, the strength and other properties are different in different direction. So this type of grain flow, here we can see in the forged component, here we have a particular grain flow structure. So maybe this type of grain flow, in this direction it has a very high strength, because the grains are arranged like this to resist any external force uniformly. Okay, so in this direction it has very good strength, but maybe in this direction that is along the grains flow, it has low strength. Okay, so that means the forged component will have an anisotropic property. So we should design the grain flow according to the final product use. For example, I am going to make a turbine blade. So for example, this is the turbine blade I am going to make for using forging process. So in the turbine, when the turbine in use, the water pressure acting in this direction. Okay, so when we make this turbine blade using forging operation, we should ensure a grain flow such that in this direction should have very high strength than that of this direction. Okay, then only it can withstand very high force during the operation. So we can design the grain flow in a forging operation according to the requirement, so that we got a product with a very high strength in that direction. Okay, so that is the this one. It is lower in particular thickness or other direction, but it has a maximum in particular direction. So it has an anisotropic nature. Then it gives a finer structure after recrystallization. If it is a hot working process, that finer crystals, grains gives higher strength as well as ductility. That is also an advantage for making different products and for the operation time of the different products. So it has an elongated grain flow structure, and this gives anisotropic property. So it will not allow crack generation and propagation. Okay, and this grain flow, even maybe our raw product which is used for the final for the forging operation, maybe the grain flow like this. But after forging, we got the shape like this. After forging, we convert the shape like this. Then the grain flow will be like this. The grain flow may be like this. Okay, so this grain flow actually undergoes reorientation. It will change the direction according to the directional compressive force we apply during the forging process. Okay, so we need to design this grain flow. Then only we got strength according to our use in the particular direction. So we got good strength and toughness by this grain flow orientation. So preferred orientation, there is a preferred orientation for each product. So we need to make the grain flow in that direction. So that is about the grain flow pattern during the forging operation.